Up until now, we've talked about simple ideal gases. And, you know, we mean two different things by the words simple and ideal. So ideal, of course, means that you're going to assume that molecules don't interact, they don't occupy volume, and all of the collisions are elastic. And that allows us to use, of course, our very well-known equation of state, right, which is PV equals nRT. And simple means that the heat capacity is equal to a constant. And we took a little bit of time in a previous lecture to actually derive an expression for the constant volume heat capacity for a monatomic ideal gas. And we did this for the constant volume heat capacity, where we said then that CV was equal to 3/2 R, right? And we basically did that just by summing the kinetic energy of every molecule inside of an arbitrary sized box. And then I did a derivation, which showed that the constant pressure heat capacity is simply the constant volume heat capacity plus R. And so this allowed us then to say, okay, if CV for a monatomic ideal gas is 3/2 R, then of course CP is just 3/2 R plus R, which is 5/2 times R. And we did the same thing, or we didn't do the derivation, but then we talked about the new modes that a diatomic molecule can store energy that a monatomic compound can't. And so that gave us an extra R. So the constant volume heat capacity for a diatomic simple ideal gas was equal to 5/2 R, and the constant pressure heat capacity was then 7/2 R. And these two especially, if you could commit those to memory, that would be great. I don't encourage people to just blindly memorize a lot of things, but knowing these will come in handy. And of course, we also said, okay, for a triatomic simple ideal gas, then the constant volume heat capacity would be 7/2 R. The constant pressure heat capacity would be equal to 9/2 R. Okay, and we kind of stop there because as molecules get larger and larger and larger, some of these assumptions that we make about how they interact with each other may be invalidated. Also, the different modes that molecules store energy, whether it's kinetic energy, vibration, rotation, spin, it becomes more and more and more complex as the molecule gets larger. So first of all, we can't just keep adding R's forever. And second, as we change the temperature, you're going to sort of store energy in these molecules in different ways. So you can't just vibrate, for example, at any frequency that you want forever, right? And just increasing the frequency of a vibration doesn't necessarily work. So the balance between these modes of operation will change as the temperature changes. And so this really calls into question our assumption of a simple ideal gas. So in real life, are these heat capacities really equal to these constants that we have here? Okay, and one of the best ways I think to visualize that is to plot the heat capacity, either one of them, as a function of the temperature. And your book does that. So in chapter 4, right, so figure 4.1 actually plots the constant pressure heat capacity as a function of the temperature in Kelvin. And one of the things that you can see here is actually for argon, where it's a monatomic ideal gas, where again, you just store energy in terms of motion. Actually, think about what CP was on the on our document just a second ago, right? It's 5 halves R. So the plot here is CP divided by R. So CP should be equal to 2.5. And that's exactly what you see here for argon. That assuming that argon is a simple ideal gas appears to be fine. Now for nitrogen, right, a diatomic gas, the heat capacity does change as a function of temperature. And the interesting thing here is that we expected it to be equal to 7 halves R, right, as a simple diatomic molecule. And we do. We start at lower temperatures right at about 3.5, right, or 7 halves R over R equal to 3.5. And it's relatively close to that number up until maybe about 800 Kelvin. And then it really does sort of linearly deviate from there. And you can get up to 1500 K or so, and you're at almost a value of 4. Then you have triatomic molecules like CO2 and water, where we just said on the previous slide that we should be equal to about 9 halves times R, or CP over R equal to 4.5. And CO2 starts at 4.5 at really low temperatures, then deviates from that very, very quickly. And then water, interestingly, starts at a value below 4.5, and then also increases with the temperature. And so hopefully some of this, right, especially water, jives with what we were talking about previously, that we wouldn't expect water to be well described by some of these very simple assumptions that we've had before. Now, the interesting thing about this plot is you might think, oh, that means it's not behaving as an ideal gas. But you'll note that I never said that. It is true that water isn't well described by the ideal gas equation of state, but actually it's not so bad for CO2. And this deviation of the heat capacity with temperature doesn't actually speak at all to whether the ideal gas equation of state is good or bad for describing the behavior of the fluid. Those are two totally different things. And that's one of the reasons why I started there at the beginning of lecture today, was that assuming that it's an ideal gas and assuming that it's a simple gas are two totally different things, and we'll treat them that way this semester. But one of the things that you're going to notice is that in all of the systems where we are considering air, well, if we're doing it at high temperature, we have to now consider this change in the heat capacity. If we start to look at molecules like CO2 and water, which we're going to do combustion reactions very, very soon here this semester, and combustions naturally heat gas, right? So we're going to have to account for heat changes during combustion reactions. So obviously now we're going to have to find some kind of framework to take this change in the heat capacity into consideration. And in previous lectures, right, we've said that delta U is equal to the integral from T1 to T2, right, of CV dt. And we've said that, and if I'm actually going to write these both as the intrinsic form, that's delta U. So then delta H is equal to the integral from T1 to T2 of Cp dt. Now you'll notice your book doesn't report it as CV and Cp. And if you actually go back into the appendix in the back of your book, they also don't report things as CV and CP because they want to be unit agnostic. Some of us want to use SI units, right? Like joule per mole Kelvin. Some people won't want to do that. They'll want to use, kilojoule per kilogram Kelvin or BTU per pound mole Rankine. And if you then normalize CV and CP to R, and they have the same units, you come up with something that's dimensionless. So your book actually describes the temperature change of these ideal gases as the heat capacity divided by R. And of course, they only give the constant pressure heat capacity because even though both of these deviate with temperature, we derived a fundamental relationship between CV and CP that isn't broken just because it changes with temperature. So what that means is that this relationship is always true for an ideal gas, And so even when we have these functions where the heat capacity is allowed to change as a function of temperature, we actually can use that relationship between CV and CP to get the one that we want, depending on the calculation that we're doing. And in your book, all that they've done is they've taken experimental data and they've fit polynomials to experimental data. So there's nothing really fancy that was done there. So the functional form that they give is just A plus BT plus CT squared plus D divided by T squared. And there's nothing fundamental about that whatsoever. Like I said, all that they did was fit data. So now in our class, if we're going to take the temperature change into consideration, right, if it's not a simple gas, now if we were going to calculate delta H, and we want to do this in a unit that we actually care about, we're actually going to solve this as equal to the integral from T1 to T2 of Cp over R, which is a function of temperature, times R dt, right? And of course, these two R's will cancel, and that still just becomes the integral of Cp dt. And that R is going to come outside of the integral, and so that's just R times the integral from T1 to T2 of Cp over R dt. So if we were to actually do that, right, so delta H is R times the integral from T1 to T2 of A plus BT plus CT squared plus D divided by T squared dt. And the very first lecture that we had this semester, we actually worked on taking this integral. So delta H then is equal to R times A times T2 minus T1 plus B over 2 times T2 squared minus T1 squared plus C over 3 times T2 cubed minus T1 cubed minus D times 1 over T2 minus 1 over T1, right? So there's delta H, essentially to heat a non-simple ideal gas. Okay? Does anybody have any questions about that?
Do you have examples of non-simple ideal gases?
Well, I think if we go back here, water and CO2 and nitrogen are, I mean, nitrogen in this low temperature range is pretty close. Water might not be an ideal gas, but CO2 is a pretty good example of a non-simple ideal gas. Methane also behaves a lot like a non-simple ideal gas. We don't actually have a relationship for a 5-atom ideal gas where we would assume the heat capacity is equal to a constant. But if you think about it, methane is way above its critical point, or way above its critical temperature at least. And so you would expect the ideal gas equation would apply very well to methane, and it does until you get to super high pressures. And then the heat capacity for methane is definitely not constant. So that's probably a good one that we're actually going to use this semester, because our first combustion problem we'll do either in the next lecture or the one after that is going to be a methane combustion. So that's a good question. So what I think would be an interesting thing to then do is to go back and explore 2 problems that we've already done this semester, where we've calculated things like work, heat, etc., assuming that this thing was a simple ideal gas, and lift that assumption that it behaves as a simple gas, okay? And then to compare what the result was from today's lecture versus that previous lecture. So the first one I would like to look at was from lecture 6, where we had oxygen in a flexible vessel, right, that was in mechanical equilibrium such that the pressure was just equal to atmospheric pressure. And then we heated the gas from 25 degrees C to 450 degrees C. And if you remember, since we're going to do this at constant pressure, how we ended up calculating the work was relatively straightforward, and we'll do that in just a second. And then we were able to calculate the heat that was transferred because we know at constant pressure that Q is equal to delta H. Okay, so then that tells us we're going to end up taking the integral of Cp dt. So then we'll just have a look at those two. And then what we're also going to do in our second example is to revisit the heat exchanger problem that we did in our last lecture and to see what changes this non-simple ideal gas would have on the final temperature that left the heat exchanger. Okay, all right, so let's do those two. And let's start here with oxygen. And let me bring up the notes. All right, so here we have oxygen, flexible vessel, heated from 25 to 450 degrees C. So we want to calculate Q, W, and the specific volume. Now, of course, the calculations that we made for the specific volumes aren't going to be affected at all by anything that we've done in this problem because we're still assuming that the gas is an ideal gas. So our initial specific volume is still equal to RT over P, right? And we did that calculation previously. And so we know that 0.08206 liter atmosphere per mole Kelvin times the initial temperature, right, which is 298.15 Kelvin, divided by the pressure, right, which, we know we're operating at 1 atmosphere. And so we calculated that that was 24.5 liters per mole, right? And then we calculated the final volume. And because the pressure is equal to a constant, right, we have that, P final, V final over P initial times the initial specific volume is RT final over RT initial. So right, those cancel. And what we're left with is just a simple relationship that the final specific volume is equal to the initial specific volume times the ratio between the temperatures, right? T final over T initial. So that gave us 24.5 liters per mole times the final temperature was 723.15 Kelvin, then divided by 298.15 Kelvin. And that still gives us the same answer here, right? We're at 59.3 liters per mole. And our expression for the work is still equal to minus the integral, right, of PDV from V1 to V2. And our pressure here is equal to a constant. So that just becomes equal to the pressure times V2 minus V1. And if you remember, we plugged in the two numbers, we changed the units and to kilojoules per mole, and that's minus 3.53 kilojoules per mole. So this assumption of a simple gas hasn't changed anything with regards to the final volumetric specific volume, of the final state or the work. So those relied on the ideal gas assumption, not on this thing where you're assuming that it's a simple gas. So the only thing that's going to change here is that, remember, when the pressure is equal to a constant, Q is equal to delta H. And that is what's going to change here, right? So if Q is equal to delta H, so we just did this a second ago, where we have an expression for delta H, right? And that's this thing up here, right? So that's just equal to R times, right? A times T2 minus T1 plus B over 2 times T2 squared minus T1 squared plus C over 3 times T3 cubed minus, oh, sorry, not T3 cubed, that doesn't exist. T2 cubed. Sorry, I got a little excited about the threes. T1 cubed minus D times 1 over T2 minus 1 over T1. And so all we need to do then is to go find these constants for oxygen in the appendix. And so for oxygen, A is actually equal to 3.639. B is equal to 0.506 times 10 to the minus 3. C is equal to 0. And D is equal to minus 0.227 times 10 to the 5th. And one of the things I would like you guys to do sometime after lecture today is to go into the appendix and see how these constants are reported. So you'll notice that in the appendix, in the table, this will be listed as 0.506. And above it in the column, it'll say B times 10 to the 3rd. And so I just don't want you to confuse that this means that B is 0.506 times 10 to the 3rd, right? It means that the value that they report has been multiplied by 1,000. So that's why that's times 10 to the minus 3rd. And they do the same thing with D. And they might do it with C as well. I just don't remember. Okay, so just make sure that you're comfortable with that. And so if you plug those values into this equation and solve for Q, actually you find that Q is equal to 13.40 kilojoules per mole. And in the previous lecture where we solved this problem, right, lecture 6, we actually found that Q was equal to 12.4 kilojoules per mole. And so they're definitely different, right? If we just assumed that the constant pressure heat capacity is 5/2 R, that's what you get. And that always, at least for me, leads to a question of, is that significant? What do you guys think? Is that a significant difference?
I would say because it's in kilojoules, probably it would be a significant amount.
All right, anybody else? Anybody want to disagree strongly about Qs? I mean, I think the answer to things like this are, it depends, right? It depends on what it is you're looking at. So if you're heating up oxygen, and you have to very precisely meter the temperature, and you designed around adding a certain amount of heat to the system, this could be significant, right? You add 13.4 or 12.4 kilojoules, you underheat the system if you actually designed it around this 12.4 number. Or maybe you did a cost analysis that was based on the fuel that you're using to do the heat, which almost always, if you're going to heat something, is either an electric heater or you're going to burn some fuel like methane. And so who knows, you could throw off your cost analysis by having, what is this, about an 8% difference between these two numbers. And so if it's a major part of your cost, yes, it might be a big deal. So I think here we very clearly see that they're different, but you as the practicing engineer are going to have to be the one that decides if it matters. And you might even wonder, well, how do I know if I have to take this into consideration? Well, oxygen behaves a lot like nitrogen. So we can go back here and look at this and think, where are we on this plot, right? We were changing the temperature between, 300 K and, 450 degrees C is what, 723 Kelvin. So we're right in the range where you're definitely on this linear upward slope in nitrogen, and it would be the same for oxygen. So, I mean, obviously there's some deviation And if the calculation isn't too complicated, taking it into consideration is probably a good idea. Okay. Now, the next example I actually think is much more clear cut whether it matters or not. And this is our heat exchanger example that we had in the last lecture, where we basically wanted to cool down this effluent, and here I'll make this a little bit bigger so you guys can see it better, that we wanted to cool down this effluent from a combustor where we know that we had a 2-to-1 ratio of water and CO2, that's the green stream at the bottom, that we really just want to be able to expel to the atmosphere, or that we want to cool it down. And we're doing that by taking water from a river that then we just want to convert into steam using the heat of vaporization of water, and then to be able to expel that to the atmosphere. And hopefully you guys recall that the solution to that energy balance that we had last time was essentially that delta H, right? This was an open system, and we got to a point where our energy balance was really that the sum of m dot times delta H was equal to 0, right? That was the solution to our energy balance. And then we said, well, we're going to do the molar version, right? So we had, the molar flow rate of each of those species times delta H was equal to 0, was the result of our energy balance. And from there, we solved this problem and found that the temperature that was leaving was equal to 420 degrees C, which is 420 Kelvin, which of course is equal 147 degrees Celsius. Okay. So if we revisit this, except now each of these delta H's are the integral of Cp over R dt, right, from T1 to T2 times R, right, to get these same units. Where are we going to be at the end of that? Well, all right, fine. So this becomes then 0 equals the molar flow rate of CO2 times R times the integral from T1 to T2 of Cp CO2 over R dt plus the molar flow rate of water in the blue stream, or here, hold on, the green stream, times the integral, or times R times the integral from T1 to T2 of Cp for water, right? And this is in the gas phase, over R dt plus the molar flow rate of water in the blue stream. And then we had two terms that were here, right? One was delta H of vaporization, right, at 25 degrees C, plus then R times the integral from T1 to T2 of Cp of water in the gas phase over R. And I'm running out of room a little bit here, so let's see if I can. Well, I almost got all of it. There we go. Sorry, guys. Let me clean this up a little bit. dt. Okay. All right. So before I move on, is this okay? Right? Does this make sense? It's pretty similar to what we were doing last time. All right. So I have this equation. Now what am I going to do?
Find your constants in the back of the book.
Exactly. So that's the next thing that I would do for sure. So we know, right, we have two species, right? We have CO2. Oops, sorry guys. We know that we have and we're heating gases in both cases, right? So we have CO2 and we have water. And so we have A, B, C, and D. So for CO2, A is just 5.457. B is 1.045 times 10 to the minus 3. C is equal to 0. And D is minus 1.157 times 10 to the 5th. And we've already, I guess we didn't do water, we did oxygen before, sorry about that. So water is 3.470. B is 1.450 times 10 to the minus 3. C is equal to 0. And D is 0.121 times 10 to the 5th. And for each one of these integrals, right, we still have Cp over R is equal to A plus BT plus CT squared plus D over T squared, right? So CPI is just AI plus BTI plus CI squared is DI. So that integral from T1 to T2 is again just equal to A I times T2 minus T1 plus BI over 2 times T2 squared minus T1 squared plus CI over 3 times T2 cubed minus T1 cubed minus DI times 1 over T2 minus 1 over T1. And for CO2 and water in the green stream, that the initial temperature, right, Ti, is 875 degrees C, and T2 is 325 degrees C. And then for the water coming in the blue stream after it's been vaporized, we have TF, right, this thing that we're trying to solve in red on the left, and then the initial gas temperature T1 is 25 degrees C. So last time when we did this in class, I just showed, well, okay, we can solve this relatively easy by hand, right? Because you can get an easy expression that says that T final is equal to something. But can we get a nice algebraic solution to this where we're just going to come up with T final is equal to something that's easy for us to compute?
No.
Yeah, I mean, definitely not, right? So, okay, what do we need to do here? How are we going to solve this problem? Anybody?
Maybe graph it, but I don't know if that's really a good idea or not.
Hey, graphing is actually, quite frankly, graphing is a reasonable option. The thing is that, so just think about this. Each one of these integrals is going to have a bunch of terms, right? So graphing and seeing where you get the solution equal to 0, I'm not going to say is an unreasonable approach. It's not. I guess it depends on where you would want to graph it, but there's something else that we've talked about using earlier in our class that actually we
Probably
kind of naturally
solver,
built
right?
for this. Yeah, we could either use solver or remember here we have one variable, one unknown, right? So you can use goal seek in Excel, right? Set up an Excel spreadsheet where we put in all of the information that we know about all of the gases, and then we can calculate the value of all of these terms, right? Or maybe if you want to highlight these, and then we actually can set a cell equal to 0 by changing the final temperature, right? So we can have a cell that is our energy balance and just let Excel iteratively solve this problem for us. And so that's what I do every time I see a problem like this, where I know that this is going to be a highly complex function. So I'm going to set up an Excel spreadsheet and I'm going to use goal seek to solve this problem. So here, let's let's do that really quick and then just ask a couple of other questions. All right, so let's pull up Excel, which I already did. All right, so here's my Excel spreadsheet. And what I've done is our green stream, right, which is the combustion effluent, is at the top here, right, where I have the flow rate of CO2, the molar flow rate of CO2. I have the molar flow rate of water. I have the inlet temperature, the outlet temperature, and then I simply have two cells where we're calculating the enthalpy change when, that I have this enthalpy change with water and CO2, and you'll see that the values for CO2 and water that we pulled from the back of the book that we wrote just a minute ago are here on the right-hand side, okay? So, all right, so we have two formulas where if you look at this, this is just minus N, right? So if this is CO2, B3 is the molar flow rate of CO2 times R times that integral, right? L2 is A, right? Then times D3 minus E3, which is T2, or actually that's T1 minus T2, but you'll notice I have a negative sign in front of it. Don't ask me why. And then I did the exact same thing for water. So we have sort of N dot delta H for both of the components in the green stream. And then the blue stream, where we have steam coming in from, or water coming in from the river, we have delta H of vaporization, which isn't affected at all by our assumption about the heat capacity. And then we have 3.5 moles of water per second. And then we have our initial temperature coming in. And I thought that the best initial guess here would be our answer from the last time, where we assumed that the heat capacities were equal to a constant. And then here we have N times the heat of vaporization. Here we have NR times the integral from T1 to our guess. And then we have some calculated value for delta H, which is just the sum of those two. And then here's our energy balance, which is just delta H of CO2 plus delta H for water plus delta H for water in the blue stream. So that cell is just this part of that equation, okay? And so now I have this, I have one guess or one unknown and one equation. So here in I8 is the result of that equation. So obviously our exiting temperature is incorrect, right? So now we have to solve this problem. So what I did was I used goal-seek to change this value. And unfortunately, in the iPad version of this, goal-seek does not work particularly well. So I goal-seek this before class, and it was 961.56 Kelvin. And you'll notice that, okay, the result of the energy balance, I didn't do it to, 9 digits like they would, but that's 0, right? So essentially what we found is that T out is 688 degrees C, okay? So when we do that, so T final is equal to 961.56 Kelvin, which is 688 degrees C. All right. So remember the context of this problem. We wanted to take water from a river, and we wanted to use the heat of vaporization to cool down this gas that was coming out of a combustor. And then we want to just let the steam go out into the environment, right? The stream that's coming out of the top right of blue here would be just water vapor. So if we submitted this plan to a city, would they let us eject steam at 700 degrees C into the atmosphere?
No.
We could kill all kinds of wildlife that way, particularly birds, right? Because you're going to let heat out at the above where people walk. And so if you started blasting 700 degrees C steam, anyway, you would kill so many birds, you'd be on the news. So, all right, that's not good. So obviously, we need to reduce the temperature that this steam is leaving our system. So let's think about this from a practical perspective, right? We can't move the plant, or we can't use anything that's not water. So how are we going to decrease the exit temperature of the water using the variables on this spreadsheet that we have control over? What would you do as an actual practicing engineer?
Didn't you run the gas up through a column of the liquid water? Cool it down?
So what would that do? So we drew our system all the way around this box, right? Or all the way around the heat exchanger. So as long as the flow rate of water was equal to 3.5 moles per second, and we were operating at steady state, the length that those two things interact doesn't matter, right? Because you're thinking of length and flow gives you more time or more contact or something. But remember, we can't say anything about time here. So we're assuming that we have a semi-infinite time, right? We reached equilibrium. So there's something else that we have to do here, right? The geometry, because of the way we define the system, isn't going to help you. Anybody else? What could we do? There's one very, very simple thing to do.
Add more water?
Add more water, right? Water is cheap, right? We built the plant next to the river to have an infinite supply of cold water that we wouldn't have to pay a lot for. And so if we were going to add more water, right, that would just simply be increasing the flow rate of water, right? So I don't know. I'm going to pick a number. Actually, I will say an hour ago, I picked a number and said, well, what would happen if we increase the flow rate of water from 3.5 moles per second to 5 moles per second? Well, now we would do the same thing, right? We would have to make we would have to goal seek this, which of course I did. And all right, let's say that this was 412.618. And there it is, right? We solved the energy balance. So now we're letting steam go at 140 degrees C, which is much better and actually acceptable here. So we had a couple of examples today where we're able to change or to lift an assumption about the heat that's required for a desired process to happen, right? Where we never lifted the assumption that we had an ideal gas, but we lifted the assumption of whether it was simple or not, which meant we allowed the heat capacity to change. And in the first example, it was sort of borderline whether it mattered or not. But in this example, it really mattered with the solution. Now, how you would respond to that in the real world is very simple. You would just meter more water into the system. And so, feeding liquid water into a heat exchanger and slightly increasing the amount of water is a relatively straightforward thing to do. But then again, what if you had to buy a pump to do this? And now to get the flow rate high enough that the exhaust temperature is acceptable, we had to actually increase the flow rate by about 40%. So you could grossly undersize a pump. And in a large process, you might think a water pump costs $100 that you might use at your house or, in a well. But if you're talking about a large industrial size process, you're talking tens of thousands of dollars for a large pump, plus installation costs, maintenance, and all of that kind of stuff. So here's an example where in a very practical system, you could have very, very serious ramifications for not taking the temperature change or the heat capacity change with temperature into consideration.